Hey, what is good, chat? Today we're getting a math stylus, and really, our math stylus is gonna help us with one main thing, and that is uh, understanding weird looking functions. Let's graph something out. Let's have the graph go like this, right? Okay, wait. I have an idea. Boom, right? And then, let's say that is the rest of the function. Let's give some coordinate points. Let's say this is x equals 2. This is y equals 3. And this is y equals 5. Here, let me make that a bit thicker. And that is not what I did. Thank you, OneNote, for being fully functional with my tablet. Okay, now let's look into it. If I were to ask you, wait, you know what? That is not what I meant to do. Okay, no, I see how it is, OneNote. See, you want to go and ruin my own work. Let's say this is x is equal -2. This is obviously 0, and this is 0. Okay, let's quick review. What is f of -2? That means look at x equals -2 and see its output. Here we see it's 3. If I asked you f of 0, take a second. That's more than a second. F of 0 equals 3. But what if I asked you f of 2? See, now you'd be confused because we have two key things here. We have this imaginary output, or not imaginary, but a undefined output, and we have a real input up here, which is 5. So the correct answer for f of 2 would be 5. But really, what does it mean? Like, what is really happening here? And then, in order to better understand this, we can look at the really conceptual limit. And what I mean conceptual limit is that for the concept of approaching x equals 2, what is really happening here? And we can use limit notation. Limit notation would be lim. And then we're approaching x equals 2. So we have x approaching 2. And then we have, I don't have a function for that. Let's just say f of x. So what is happening when x is approaching 2? And in order to understand this, let's look at both sides of x equals 2. Let's look at lim as x approaches 2 minus. And the reason we say, that is not anywhere near what I was trying to say. The reason we say minus is really because we're looking at a value slightly less than 2 infinite. I think the word is infinitesimally. But basically, we're looking at this super tiny value right there. And where that's being approached conceptually. It doesn't even have to be existent. It's just really where it's being approached. And let's say that is around x equals 2. I mean, y, like, a equals 2. And if we look at the right hand, which is always going to be greater in x, which is 2 plus, we see that it's equal to 5 around up here, which is slightly left to 2. And there it's equal to 5. So if I were to come up with a number that the limit would be approaching, I would have to say that the limit itself does not exist, as both sides are not coherent. This lack of mixing and matching up really there's no proper value of limit to get. There's no conceptual way to approach this because it's so different from both sides. And that's really the thing with limits. They truly are confusing, as it's all concept. It doesn't have to be algebraic. You just really have to see what is being approached. And we can even do this algebraic. We can even do this with a proper graph. Let's say if I was to draw this variant of that graph, this would still be 5. Or we're making this 5 now. And we have an empty circle here. But now we have this. Let's say this is still equal to 2. If I were to ask for the limit of x approaches 2, we'd first have to look at the left. Here, lim as x approaches 2 minus. We see that at 2 minus, it's basically 5. So we can say it equals 5. And at lim x approaches 2 plus, we can see that once again, it is basically equal to 5. Therefore, we can say the limit as x approaches 2 is equal to 5. Even though the graph does not exist there, we're asking what the y value would be if there was never a stop. And that is exactly what a limit is. It's all conceptual. And now we can even do that algebraically. Let's try it with this. Let's do f of x equals x squared plus 4x plus 4 over x plus 2. Now, if we were to plug in, or sorry, let me make this x minus 2 to make it make sense. If we were to plug in negative 2, oh, actually no, let me keep plus 2. If we were to plug in negative 2 into f of x, we would get negative 4 minus 8 plus 4 all over 0, which does not exist. Therefore, we can't really understand what the y value would be at negative 2. Which is why we use limits to understand these kinds of things. We can do lim x approaches 2 equals, or I'm sorry, I mean negative 2. We can firstly factor the top to see whether or not things cancel out. And we do end up getting x plus 2 and x plus 2 at the top and x plus 2 in the bottom. This allows us to factor, and we're able to find a simplified equation, which is x plus 2. And the reason we ignore the whole in this situation is that it's all conceptual. It does not matter that it's undefined. We're simply finding what it would approach if it were to even exist. And here when we plug in oh, I'm so sorry guys. I meant to make the bottom negative. And if it is negative, there's actually no simple answer. I'm so sorry for that mix-up. And if there is no simple answer, we must look at what x negative 2 would look like slightly before we even get to negative 2. So here we have negative 2 slightly smaller plus 2 times negative 2 slightly smaller plus 2 all over negative 2 slightly smaller plus 2. Here at the top, a negative 2, a slightly smaller version of negative 2 plus 2 will result in a positive number times another positive number, because those are the two. All three numbers really are the same, all over a positive number. So here we can see that we're approaching positive infinity here. Because these are all such small numbers, it's really going to end up into some huge number like infinity. And now let's look at a slightly greater version of negative 2, infinitesimally greater. And here we have negative 2 slightly greater than negative 2, plus 2, and really the same everywhere. Negative 2 plus 2. And here we see at the top we get a negative number times a negative number divided by a negative number. And that is actually a negative times negative is a positive, divided by negative is a negative number. And here we see that would basically approach negative infinity. So both sides of that equation don't add up. And that means that, once again, the limit of x approaching 2 simply does not exist. And let me pull up this. Let me pull this up in Desmos. I'm writing it up right now. X squared plus 2 plus 4x plus 4 all over x minus 2. And we see, let's switch this up. Can I switch the capture? Boom. Here on Desmos, we're able to see that the graph approaches an asymptote at that certain point. So when it is undefined, it truly has no value that it's approaching. If we were to, for example, make the denominator a root, we would end up getting the whole as the answer. When I mean the whole as in -2, this is where the whole would have existed. And this is exactly the value we would have gotten. We would have gotten 0 for the approximated limit. So really, when it does come to limits, it's all concept. And it really is, I think, hard to understand. I'm not sure if I'm the best one explaining this. But it is key to understand the fact that a limit is simply conceptual. And whatever you do approach, although it does not exist, it is what you would be approaching. And looking at both sides is focal in understanding that. And if there's no need to look at both sides, really what is left with your equation, for example, when you divide, when you see two of the root, like a root of the equation in the top, and that same thing being in the bottom, like a factor, when those cancel out, it's simply whatever y value you get there, which would be your answer. Sorry if I explained this poorly. You know what? We'll do a quick one. Here, let's do the limit as x. If only my tablet could work. If only my tablet could work. Limit at x approaches 2 at x plus 4 x minus 2 over x minus 2. Here, even though we know that there is a undefined, the graph is undefined at x equals 2, we see that there's actually a matching factor in the top and bottom. So we could do the limit as x approaches 2 equals x plus 4. And then conceptually, if the whole were to be neglected, we would see that the graph is actually going to approach y equals 6 at x equals 2, even if it does not exist there. And that is how limits work without that kind of asymptote. And you can continue to do this kind of thing with really any function. Let's look at n behavior, which can also be written in a limit-like manner. X approaches infinity. If we do x to the 4th plus 4x over x cubed plus 3, what you end up seeing actually is a division of the leading terms, as that's what really matters in the situation. And you get x cubed over x 4th over x cubed, which is equal to x. And that means that as x approaches infinity, we take the n behavior of the function of x. And if you realize that it's an odd degree and positive leading coefficient, we know as the limit x approaches infinity, it equals positive infinity for this function of x to the 4th plus 4x over x cubed. And if you have a situation where, let's say, the leading degree was higher in the denominator, let's have x cubed over x 4th, you would approach simply just 0 on both sides, as you would have some form of the reciprocal graph. And this reciprocal graph has an asymptote at x equals 0. So you'd forever be approaching 0. Which is why whenever the higher degree is in the denominator, you approach 0. That is limits, and I hope you can understand that. Please, I recommend watching other videos and really understanding limits before continuing anything else in pre-calculus or calculus. Have a great day. Stay a steppin'.